Something strange is emerging from Euclid's deepest images of the universe. It is not confined to a single galaxy, one galaxy cluster, or an isolated corner of space. Instead, it appears everywhere. Across the cosmos, Euclid is revealing subtle distortions, hidden gravitational patterns, and galaxies held together by far more mass than astronomers can actually see. Ancient red objects appear too massive, too compact, and too old to have formed so soon after the Big Bang. At first glance, these images are breathtaking. A spiral galaxy glowing through cosmic dust, a massive galaxy cluster containing thousands of galaxies, a dense field of stars near the center of the Milky Way, and tiny reddish points of light shining from the edge of the observable universe. Yet beneath their beauty lies something far more unsettling. The universe does not appear to be held together by the matter we can see. Stars alone are not enough. Gas alone is not enough. Even all the visible galaxies combined cannot account for the enormous gravitational forces shaping the cosmos. Something invisible is influencing the motion of galaxies, bending the paths of light, stabilizing structures that should have torn themselves apart long ago, and perhaps even helping the earliest cosmic giants grow far faster than current theories can explain. Euclid was built to uncover this hidden architecture, and the more it observes, the more one question becomes impossible to ignore. What is truly holding the universe together? When Euclid looks into deep space, it is doing far more than taking photographs. It is measuring gravity itself. That may sound unusual because gravity is invisible. We cannot photograph it directly. We cannot see dark matter glowing in space, nor can we point to a cloud of dark energy and identify it with our eyes. What we can observe, however, are the effects these invisible forces produce. We can watch how galaxies move, how enormous clusters remain bound together, and how light bends as it travels through regions where unseen mass must exist. This is where the mystery begins. Massive galaxy clusters, such as the Perseus cluster, contain thousands of galaxies interacting across unimaginable distances. From Earth, they appear stable, majestic, and almost timeless. Yet when scientists calculate the amount of visible matter, including every star, cloud of gas, and galaxy, they consistently find that it is nowhere near enough. The galaxies move far too quickly, and the clusters themselves are far too massive to remain intact under the gravitational influence of visible matter alone. According to ordinary calculations, many of these systems should have flown apart billions of years ago, scattering their galaxies into deep space. Instead, they remain organized, stable, and tightly bound, as though supported by an invisible framework. This unseen structure is what scientists call dark matter, a mysterious form of mass that neither emits nor reflects light and does not interact with ordinary radiation in any familiar way. Although we cannot observe it directly, its gravitational influence appears to shape everything around us. Euclid was specifically designed to map this invisible cosmic framework by studying a phenomenon known as weak gravitational lensing. This effect produces tiny distortions in the shapes of distant galaxies caused by unseen concentrations of mass lying between those galaxies and Earth. Imagine a beam of light traveling across billions of light-years in what should be a perfectly straight line. As it passes through an invisible gravitational field, its path bends slightly. The distant galaxy then appears stretched, warped, or subtly shifted from its true position. Each individual distortion is almost imperceptible, but when Euclid measures millions of them simultaneously, an extraordinary picture begins to emerge. It is not a map of light, but a map of mass, a silhouette of the invisible universe itself. This is why Euclid's images are so significant. They do more than reveal where galaxies exist, they reveal where the missing gravity must be. And everywhere the telescope looks, the same hidden pattern appears. Euclid then turned its attention toward one of the most crowded regions of our galaxy, the central bulge of the Milky Way, and captured something almost unimaginable. It created a colossal mosaic containing more than 60 million individual stars. This region is among the most difficult parts of the galaxy to study because dense clouds of dust obscure the view, stars overlap one another, and the sheer concentration of light becomes overwhelming. Observations made from Earth are blurred by atmospheric distortion, dust, and distance. Euclid, however, produced an extraordinarily precise reference map. More than a beautiful portrait, it became a cosmic grid in which every star serves as a reference point. Every point of light becomes a coordinate, and every subtle change in brightness may reveal something hidden passing in front of it. This is where gravitational microlensing becomes one of astronomy's most powerful tools. When a nearby star passes almost perfectly in front of a more distant star, the gravity of the foreground star bends and magnifies the background light. For a brief period, the distant star appears brighter than usual. If the foreground star possesses a planet, that planet introduces an additional, extremely subtle distortion, a tiny flicker, a brief anomaly that quietly reveals the existence of an otherwise invisible world. This method is especially valuable because it can detect planets that other techniques often miss, particularly cold, distant planets orbiting far from their stars. These are worlds that do not transit across their stars from our point of view, do not emit enough light to be seen directly, and remain hidden in the darkness beyond the reach of conventional detection methods. Euclid's extraordinary image of the galactic bulge serves as a crucial baseline for the future. It records the positions of more than 60 million stars before future microlensing events occur. As upcoming space missions detect tiny increases in brightness caused by these events, astronomers will be able to compare the new observations with Euclid's detailed reference map, allowing them to calculate the masses of hidden planets with unprecedented accuracy.